Picture a lamp hanging high above a flat floor. Hold a stick up in the air, and it throws a shadow straight down onto the floor below. Here is the stick, a vector reaching up into space. And here is its shadow on the floor, the point directly beneath it, where the light lands. That move, sending every vector down to its shadow on a chosen subspace, is called a projection, and it hides a single beautiful equation. Let's uncover it. Once the stick already lies flat on the floor, projecting it again does absolutely nothing. The shadow of a shadow is the very same shadow. Write that in matrix language, and it says something wonderfully compact. Apply the projection matrix P twice, and you get exactly the same result as applying it once. A square matrix that obeys this rule is called idempotent. More carefully, a projection onto a subspace does two things. Every vector it produces has to land inside you, and any vector that is already inside you gets left completely alone. It maps to itself. Together, those two facts force the equation p squared equals p. If it does no harm the second time, it did all its work the first time. Let's actually watch that. Here is the vector again, up in space, and the floor is our subspace. Project once. It drops straight down to its shadow on the floor. This green arrow. That is p times x. Now project that shadow again, but it's already flat on the floor, so it has nowhere to fall. It stays exactly where it is. Projecting twice gave the same shadow as projecting once. And that is why powers of a projection collapse. P squared is p. So p cubed is p times p squared, which is p times p, which is p again. Keep going. And p to any positive power is just p. Once you have projected, repeating never changes a thing. Let's build a real projection matrix. The simplest target is a single line along a direction vector A. The projection onto that line has a neat closed form. A times a transpose, divided by a transpose A. The bottom, a transpose A, is just a number, the squared length of A. The top, a times a transpose, is a full matrix, a matrix over a number. That is our projector. Take a equals 1, 1, the diagonal direction. Then a transposer is 1 plus 1, which is 2. And a times a transpose is the 2 by 2 matrix of all ones. Divide the matrix by 2, and there is p a half in every entry. That is the orthogonal projection onto the line through 1, 1. Does it pass the test? Square it. 1, 1, 1, 1 times itself gives 2's everywhere. And the quarter out front turns those 2's back into halves. P squared equals p. It is genuinely a projection. Now see it act. Here is the line through 1, 1, and a vector b at 3. 1, setting off the line. Project b onto the line and p sends it to 2, the closest point on the line to b. The dash drop from b down to its shadow is the error. And look how it meets the line at a perfect right angle. That right angle is the whole secret of least squares. The residual, b minus bb, is always perpendicular to the subspace you project onto. Here, 1 minus 1, dotted with the direction 1, 1, is 0. A line was one dimension. Step up. Project onto a whole plane, or any subspace, by stacking its basis vectors as the columns of a matrix A. The general projector reads A times the inverse of a transpose A times A transpose. It looks heavier, but it is the same idea. And when the columns of A are already perpendicular, a transpose A is just the identity, and the whole thing collapses back to a times A transpose. Let's do exactly that case. In 3 dimensions, let the plane be the floor, the xy plane, spanned by the first 2 coordinate directions. Stack them as columns of A. Their dot products give a transpose A equals the identity, so the columns are orthonormal. So P is simply a times A transpose. Keep the x and y coordinates, and wipe the z coordinate to 0. A projection onto the floor written as a matrix. Now watch P work in space. Here is the floor, and a vector reaching up above it. Numerically, take 2, 3, 4. The 4 is its height off the floor. Apply P. The x and y survive. The z is zeroed. So the shadow lands at 2, 3, 0, right on the floor. The dashed line straight down is the part P threw away. And that discarded part, 0, 0, 4, points straight up, exactly perpendicular to the floor. The residual is orthogonal to the subspace, just like it was for the line. Same picture, one dimension richer. The equation p squared equals p is so tight that it pins down the eigenvalues completely. Start with any eigenvector. P times v is lambda times v. Now hit v with p squared. Since p squared equals p, the left side is just pv. Again, no new information yet. But watch what the eigenvalue does. On one side, p squared v is lambda squared v. On the other, pv is lambda v. So lambda squared v equals lambda v. And since v is non-zero, lambda squared equals lambda. Rearrange. Lambda times lambda minus 1 is 0. So every eigenvalue of a projection is either 0 or 1. There is no third option, and they tell a clean story. Lambda equals 1 marks the directions that survive. They already live in the subspace, so the shadow is the vector itself. Lambda equals 0 marks the directions that get crushed to nothing, the ones perpendicular to the subspace, the part the projection throws away. Eigenvalues also hand you rank and nullity for free. Take the simplest projection. Keep the first coordinate, drop the second. Its image is the whole x-axis, so its rank is 1. What it kills is the y-axis, so the nullity is 1. And sure enough, rank plus nullity is 2, the full dimension. In general, if P projects onto a k-dimensional subspace, its rank is k, and its nullity is n minus k. One more distinction, and it is the one people trip over. When the projection drops straight down at a right angle, it is an orthogonal projection. And then, and only then, P also equals its own transpose. Symmetric. But a projection can also slide down at a slant, an oblique projection. It still satisfies P squared equals P, yet it is not symmetric. So idempotent alone does not mean symmetric. Symmetry is the extra badge of an orthogonal projection. Let's meet a projection that shows up everywhere in data. The centering matrix. Let 1 be the column of all ones. Then C is the identity minus 1 over n times 1 1 transpose. What does it do? Multiply any vector by C, and it subtracts the mean from every entry, recentering the data around 0. For 3 items, C works out to 2/3 down the diagonal and minus a third everywhere else. It is clearly symmetric. And because 1 transpose 1 is just n, the cross terms collapse and C squared comes right back to C. So C is symmetric, an idempotent, an orthogonal projection. Let's enter a real vector. Take 4, 1, 7. Its mean is 4, dead on. Subtract 4 from each entry, and see x becomes 0, minus 3, 3. Its coordinates now sum to 0. The mean has been removed. Add them up. 0. Every centered vector lands in the mean 0 subspace, and in n dimensions, that subspace has dimension n minus 1, one direction sacrificed to the single constraint that everything sums to 0. Your turn. Here is a matrix P, 0, 0, 0, 1. Pause the video now and answer 3 things. Is it a projection? What is its rank? And what are its eigenvalues? I'll wait. Here's the walkthrough. Square P, a diagonal with 0 and 1 squares to itself. So P squared equals P. Yes, It is a projection. This one keeps the y-axis and drops the x-axis. So its image is the y-axis, and its rank is 1. Nullity is to -1, which is 1. And the eigenvalues, as always for a projection, are 1 along the kept y direction and 0 along the discarded x direction. If you got all three, you have truly got this. Trap 1. Assuming p squared equals p forces p to be the identity. The identity does satisfy it, but so does every projection onto a smaller subspace. There are many idempotent matrices, not one. Trap 2. Thinking every idempotent matrix is symmetric. Symmetry is the mark of an orthogonal projection only. Oblique ones are idempotent but not symmetric. Trap 3. Mixing up projections and reflections. A reflection undoes itself, so it squares to the identity. A projection squares to itself. Once shadowed, it stays put. And trap 4. Eigenvalues of 0 and 1 are necessary, but not sufficient. Seeing those values does not by itself prove p squared equals p. You still have to verify the equation. Let's lock it in. A projection is any matrix with p squared equals p, idempotent. It sends every vector to its shadow on a subspace, and the shadow of a shadow is unchanged. From that one equation you read off almost everything. The eigenvalues are only 0 and 1, and rank plus nullity fills out the full dimension. Add symmetry, P equals its transpose, and the projection is orthogonal. Its residual meets the subspace at a right angle. The centering matrix is the everyday example. It removes the mean and projects onto the mean zero subspace. Master those lines, and projections will never look mysterious again.